All right, so this chapter is about oscillations. This is a very important chapter. If you're a practicing engineer, you'll see this all through your life. Okay. So let me show you a simulation of oscillation. So this is the typical oscillation that we'll study. All right, so we'll attach this mass to a spring. Okay. And here's the thing that the spring does. If you pull this mass, this is the equilibrium position. If you pull it away from the equilibrium position, what does the spring do? It pulls it back towards the equilibrium. If you compress the spring, it pushes the object towards the equilibrium position. Okay, so that's the first thing you need to have for an oscillation. You need a restoring force. Okay. All right, so let me right away point out. Okay, so here's the system. You have a mass attached to the spring. This is the equilibrium position. If you have the mass over there, then it won't move. You pull the mass to the right, and the spring pulls it back. If you compress the spring pushes it. All right. Now, the magnitude of this force for an ideal spring turns out to be proportional to the displacement from the equilibrium position. Okay. This is what we're going to study. The restoring force is proportional to the displacement. Okay. So, for instance, this problem is too hard. X to the power anything else is hard. Okay. We're going to study a restoring force that is proportional to the displacement. Now, here's the neat thing about this motion. Okay, let's say I pull it over to the side this far and then let go. It'll oscillate like this. Okay, the same system, let's say I pull it this far and let it oscillate, it'll oscillate like that. Okay, so let's say it's starting to oscillate from here. This is called one oscillation. And the time for one oscillation is the period. Okay. Now let me make this thing oscillate with a smaller amplitude. Which one will take greater time? This one or this one? It's the same. Okay? So if the restoring force is proportional to the displacement, the time taken for the oscillation is the same. So now you could use this for a timing device. Okay? Yeah, so we'll study that. The period of oscillation is independent of the amplitude. That's the beautiful thing about this. Okay? All right, so let's look at that. So for a system to oscillate, what is it that you need? You need a restoring force. So for instance, let me give you a counter example. So let's say you have a marble on top of a hill. If I disturb this marble from this equilibrium position, the forces that come into play are driving the system away from equilibrium. They're not restoring it. Okay. On the other hand, a marble in a valley, if you disturb it, then the forces that come into play are restoring forces. Okay. That will oscillate. But for the period to be independent of the amplitude, the restoring force needs to be proportional to the displacement. In this case, the marble's case, it won't be like that. Okay, so the period won't be independent of the amplitude there. Okay. All right, so what else do you need for an oscillation? So here's another thing you need for an oscillation. Okay, so let's see. When I stretch the spring, it has potential energy. Okay, and that potential energy gets converted to kinetic energy and back and forth. Okay, so whenever you have a system that is oscillating, okay, so we don't want any damping. What is damping? Friction, that is removing, turning good energy into heat. Very good. You answered before him. No, I was talking about him. I was talking about Caleb. Yeah, I knew that. You knew that. Okay. All right. So here's another thing that needs to happen for a system to oscillate. There need to be at least 2 or 3 different kinds of energy. At least 2 different kinds of energy. So whenever the system is oscillating, it's converting energy, one form of energy to the other, and then back and forth. If there is damping, go ahead. Okay. So for a system to oscillate, there needs to be 2 kinds of energy at least. Okay. So energy is cycling from one form to another. And as long as there are no dissipative forces, so these are all mechanical energy. See, that's kinetic energy, that's gravitational potential energy, that's elastic energy. Okay, so in this system, there's 3 kinds of energies. In the horizontal spring oscillator, there were only 2 kinds of energy, potential and kinetic energy. Okay. So as long as there are not dissipative forces, these constitute mechanical energy. Dissipative forces, friction, all it does is it converts mechanical energy to heat. Okay, and then the oscillation dies. And so let's kill this oscillation. You see, as soon as you have friction, it killed the oscillations. Is this good? That friction is good? Is it good? Well, if this was your motorcycle wheel and you hit a pothole, then you want damping. You want that oscillation to die. If that was a building that was shaking because of the wind, if it was a bridge that was shaking because of the wind, you want to kill that oscillation. Okay. All right. So the chapter is laid out as follows. We'll talk about simple harmonic oscillators. Those are called simple harmonic oscillators, and then we'll add damping to the system. Okay. So all tall buildings, all large structures, you have to build in damping, so that when nature sets things on oscillation, you want to kill those oscillations. Okay? You don't want the oscillations getting out of hand. Okay, again, make sure you understand this chapter. This is very important for you. Okay, so we'll look at periodic motion, a motion that repeats itself and has the same period. And when the restoring force is proportional to the displacement, that motion is called a simple harmonic motion. Okay. So what we'll be interested in is, so you pull this mass to the side. What we want to know is the position of this guy as a function of time. That gives you the configuration of the system as a function of time. How does the system evolve? Okay. And for simple harmonic motion, this will be given by a sine or a cosine function. Here's the amplitude of oscillation, cosine. Omega is the angular frequency of oscillation. Okay. We'll learn all of this. Okay. So this guy his position will be given by a cosine function or a sine function. Okay. For simple harmonic oscillators. You'll be amazed. You will see several different systems that look very different, but they're all oscillating in simple harmonic motion. Okay, so this occurs in nature quite a bit. All right. So that's the restoring force. Okay. So here's the system. Now, here's an important lesson on this slide. What you'll learn is the following. So you guys, how many of you are in differential equations? Okay. Nobody. Okay, you will be taking differential equations. Okay. And so this will tell you why you'll take differential equations. Okay, this slide will tell you. So here's a system. You want to study the system. How do you study the system? You can go upstairs to the lab, set it up, buy timing devices, get your hands dirty. It'll take you a long time to study the system. We'll show you another way of studying this system. We'll make a mathematical model for this system. Okay, when you want to study this system, what is it that you want to study? You want to know if you disturb the system, you saw that it oscillates. You want to know the position of this mass as a function of time. That's what you want to know. Okay. Remember, once you have the position as a function of time, you can calculate its velocity, its acceleration, and all kinds of stuff. Okay. All right. So what we'll do is we'll set up a mathematical model for this, the behavior of this system. Okay. To set up a mathematical model, you have to input physics in it. All right. All right. So we already studied what goes in last. Okay. So if you disturb this system, what happens? The spring exerts a force trying to bring it back. There is the force that the spring exerts, minus kx. Okay, so here is the physics. And what does Mr. Newton say? You apply a force on any object, then that object will accelerate. That'll equal the mass times the acceleration of the object. What is the acceleration? So mass times d square x by dt square equal to minus kxt. There you go. There is a mathematical model describing the behavior of the system. So you disturb the system, this position, the evolution of the system must obey this equation. What is this? This is a differential equation. Okay, so that's why you study differential equations. Whenever you model systems, this is just one very simple system, but this is what you'll start off with. You want to mathematically model a system. The equation you'll come up more than likely will be a differential equation. Okay? And let's massage this equation and write it in standard form. Okay. So this is so d square x by dt square plus k by mx equal to 0. What I did was divided by m, then brought it over here. Okay. And what is k? K is the spring constant. What is m? M is the mass of this object. Is k positive? K is always positive. How about m? Is m always positive? Okay, m is always positive. So this guy is positive. So to emphasize that fact that is always positive, we'll write it as omega squared, just some constant. Okay. Okay, so there is the equation. Okay. So what we are saying is, no matter what you do to this mass, hit it with a hammer, kick it, pull it 100 feet, and let go. Its position as a function of time needs to satisfy that differential equation. Okay? And you just solve this differential equation. So you learn how to solve these differential equations. Okay? Yeah. So there's the differential equation. Okay, now when you solve differential equations, initially you start off by guessing answers, and then you learn techniques in doing that. But, a lot of it is guessing. And then as you get familiar with more equations and learn little tricks, okay, you get better at guessing. Okay, so here's a solution that was pulled out of a rabbit hat. Okay. Well, how do we know it's correct? Well, plug it in and find out. Okay? You can always check. Now, here's a couple of things I'll tell you about this solution. Okay? So here's this equation, and there's omega. And we tell you here's the solution. That is, no matter, so you could pull the mass here and then push it in this direction and let go and it'll oscillate. You can pull the mass here and then kick it in this direction and let go and it'll oscillate like that. You can do various things. You can pull it there and just let go. Okay? All right, so keep that in mind. Okay, so here's this equation. Here's the solution. Look at this. This constant A, well, it's not in there, that equation. Look at this fella. Where did this guy come from? He's not there. All right, so here's the deal. So this is a second order differential equation. Okay. It's a second order linear differential equation, but we'll come to that in a second. The highest derivative is a second order. Okay. If the highest derivative is a second order, then you'll have two constants that are determined by initial conditions. Okay, so you'll have two constants that show up that are not in the original equation. So if this was a third order differential equation, how many constants would you have? 3. If you had 4, if it was a fourth order differential equation, Winnie, Caleb can't answer that, so we are dependent on you. All right, so this is a second order linear differential equation. Okay, so the second order, is the highest order of the derivative in there. The linear means all these terms are linear. So this is not an x squared, this is not an x squared. Okay, this is not a square. Those problems become very hard to solve. Okay, so right now, so when you have a nonlinear equations, those lead to chaos often. Okay, so you saw that. So those are the basic things about this differential equation. Okay. Now this is that equation, and when you do your differential equation class, this is one of the first equations you'll start off with. And now let me show you something. So this equation describes the behavior of this system. Here is a torsional pendulum. So this is a metal wire. This is a heavy disc hanging on the metal wire, and if you twist this disc, the disc will oscillate back and forth like this. Okay, it's a very different motion. The differential equation describing the motion is exactly the same. Okay, so the configuration of this system is measured by how much did you twist it from the equilibrium position. Okay, so you're twisting it this way, it's oscillating back and forth. And the differential equation governing that coordinate is exactly the same. Here's a simple pendulum. The configuration of this system can be measured by that angle. We are interested in, we'll disturb the system like this and let go. And how does this function behave? Okay. And the differential equation is exactly the same. D square theta by dt square. Okay. Here is something called a physical pendulum. Okay, you can take a piece of rock, nail it to the wall like that, and if you let it oscillate back and forth, this will execute a simple harmonic motion. And its equation is exactly the same. D square theta So what is changing each time? The coordinate that you use to measure the configuration of the system is changing. Omega square is changing. Omega square depends on different things in the system. Okay, but did you see that? I mean, there's so many different systems. and the behavior of all those different systems. What was the equation? It was the same equation for simple harmonic motion. Okay, so for simple harmonic motion, it's a second order linear differential equation. Okay. All right, so in this slide, what we learned was we were interested in studying a system, okay, and the cheapest way of studying this equation is to buy a paper and pencil, okay. So you have your system, you put in physics or aerodynamics or whatever it is that you're studying, you put in principles from there, come up with a mathematical model. And that mathematical model in general is a differential equation, and you study the differential equation. Okay? So here's the recipe. Here's the system. Okay, and then you put in this, and you put in a physics principle, and you get a mathematical model for the system. And after you've had your differential equation class, you get your solution. Okay. What if your solution does not agree with reality? Then you refine the principle that you put in, refine your model, and then do an iteration till you come up with a correct description of reality. Okay. All right. So again, for now, this was pulled out of a rabbit hat. You can check, you can put that in and check. Okay. So remember, we learned in our previous chapter, if you know the configuration of a system, if you know where the system is at all times, then you can calculate the velocity and acceleration, which is something that you want to know. Okay, you take the time derivative of that, and that's the velocity of the object. That's what is the velocity of what object? Velocity of this guy, okay, as a function of time. Here's the acceleration of this guy as a function of time. Okay. All right, so the position here is given by, you could have used a sine function as well. Okay, so it's given by a sine or a cosine function. Okay, and this thing actually illustrates physically that is true. So you can take a mass, attach it to a spring, and you've attached a pen to that mass. Okay, and here's how you're going to simulate time. You're going to have this paper move at a constant speed. That's going to be your time. That's going to simulate time. Okay. So as this mass moves back and forth, the pen is drawing its location. Okay. And you'll get a sine or cosine graph. Yeah.
Is that how they came up with the cosine function? They did that experiment and just...
No. I don't know the answer, but I imagine that's the problem. So you guys understand simple harmonic motion? Okay, so it's extremely important. Anytime you have to study vibrations, you bang the table, each element is undergoing simple harmonic motion. You guys have seen satellites launch, and then they'll unfurl those photovoltaic cells, and more often than not, those things are vibrating. You don't want those vibrations to get under the hand. You can analyze it using simple harmonic motion. Okay. All right, so you see, here's the period. The period is the time for one oscillation. So okay, you pull this mass this far, and then let go, and this is one oscillation. The time for one oscillation is the period. Okay? And you see the period is given by 2 pi times m divided by k. M is the mass attached, and k is the spring constant. And this makes sense. The heavier the mass, the longer it should take to complete one oscillation. And the stiffer the spring, stiffer the spring, the less time it should take. Okay, and so there it is. Okay. And here's something very interesting about it. See, this period, there's no information on the amplitude. The period for this oscillation is the same as the period for that oscillation. Okay? Amplitude is the maximum distance away from the equilibrium position. Okay? And you see, that's the very neat thing about this. The period is independent of the amplitude. Okay? Frequency is inverse of the period. Frequency just tells you how many times it will oscillate per second. Okay. Okay, so here is the system we study. Okay. You pulled it from the equilibrium position and let it oscillate. Okay. What did we learn? The mathematical model for this system was this equation, differential equation. Okay. We came up with a mathematical model that described the behavior of this system. And then we learned techniques to get the solution. Okay. So no matter what you do to this function, its position has to obey that differential equation. And here is one solution. Okay? Here's a solution to that differential equation. And so this is the position of this object as a function of time. And once you have this, you can calculate everything about the system. So for instance, you take the derivative, you got the velocity. You take the derivative of that, you get the acceleration. Okay. When do you think, so if I let go of this and it is oscillating, when do you think it's going the fastest? When is the mass going the fastest?
When the air mass is
I'm sorry?
at the peaks and valleys.
Well, so in this diagram, where will it be going the fastest?
In the middle.
In the middle, right here. It'll be going the fastest here, okay? And when it's going in this direction, the velocity is negative, and when it's going in this direction, velocity is positive, okay? So here is the velocity, and it'll be maximum. See, the only thing that's changing, the value of this guy is changing, and the maximum value it can take is 1, a sine or cosine function. So the maximum velocity is a omega, and it's negative when it's going in this direction and positive when it's going in that direction. When is the acceleration maximum? So this is a trickier question. I'm sorry?
Is it constant?
No, the acceleration is changing. See, the acceleration is a function of time. It's changing. Yeah, very good. Okay. So here's how you figure out when is the acceleration maximum. So here's the force equation. The further out you are, the greater the force on you, the greater your acceleration. Okay. So when you're at the furthest point, that's when the acceleration is maximum. Okay. So at that point, you're actually at rest. Okay. So your velocity is changing. You were going in this direction, and then you'll start going in that direction. So at that instant, when the acceleration was maximum, you were at rest. Okay. Anyway, so this summarizes it. So here's your system. Here's the mathematical equation describing the behavior of the system. Here's the solution. Okay. Now, how long will this oscillate? I'm sorry?
Forever,
Forever if
if there's no friction.
there's no friction. Okay. So that's the system we studied so far. Okay. So remember, the only force acting on our system was this guy, the spring force. There was no friction force. Okay. So next, toward the end of the chapter, we'll graduate. After we are comfortable with this model, then we'll add friction. Okay. Okay, so it'll oscillate forever without friction. Okay, so as at any location, the object has kinetic energy. The kinetic energy is 1/2 mv square. We already know its velocity, so there is its velocity, okay, as a function of time, and we're going to substitute that. Okay, so there is its velocity at any given time. Okay, its potential energy is 1/2 kx squared, and there is a potential energy at any given time. Let's add the two. This is mechanical energy. When you add these two, this is what you get. Look at this. Its velocity is changing with time, depending on where you are. Its potential energy is changing with time. But the sum of the two is not changing with time. It's constant. Okay? And so if the energy of the system is constant, that thing will oscillate forever. Okay? If you add friction, what will happen? Then this energy will decrease, and then eventually the oscillations will die down. Okay? And in a lot of your systems, you want to damp out oscillations. Okay? So, and we'll learn how to damp out oscillations. Okay? So here's so again, Winnie, when is it going the fastest?
In the middle.
In the middle. At any other location, the velocity is changing. We want to know how fast it's going given its location. Okay? And this formula gives you that. Okay? The speed as a function of the location. Okay, so it gives you the speed as a function of the position. When is it at rest? When is it at its stop? At the ends. Okay, so if A is the amplitude, here the velocity should be 0, so let's put x equal to A. X equal to A, and this will make it 0. Okay? It's going the fastest at x equal to 0. Okay? And so on. So this gives you the velocity as a function of position. All right, so we've studied the basic simple harmonic oscillator, the canonical simple harmonic oscillator, and now we'll show you other systems. I'm going to go fairly quickly because I gotta show you, we gotta do the problems as well. Okay, go ahead.
You said in the previous slide that,
I'm sorry?
you said in the previous slide
Mm-hmm.
that it's at rest at the ends.
Yeah,
What about in the middle when it's?
so that's when it's going the fastest. So when x equal to A, this would be 0, and when x equal to 0, then V is the greatest.
Or what about when, like, doesn't it stop back at, like,
No, so,
when it's done oscillating, it stops back in the middle?
yeah, but this thing will oscillate forever. There's no
Oh,
friction.
it wasn't one.
Okay.
There was friction.
Yeah, the friction will eventually make it, will stop. Yeah. All right, so now we'll study another system. Okay, and again, one of the things is you have to identify a coordinate to describe the configuration of a system. This is called a torsional pendulum. You have a stiff metal wire, and this wire goes through the center of mass of the system. Okay, and if you twist it, it'll oscillate. Okay, so if this is the equilibrium position, you twist it, you can give the configuration by measuring this angle. Okay, so this angle is, and we'll call it theta t. Okay, this is similar to this. Remember, this was x, and as this thing is oscillating, the configuration of the system is given by this coordinate. Okay, so just like that, the configuration of this system is given by this coordinate. All right, if you test this out, what you'll find is the greater the angle, the greater this wire has twisted, and it'll apply a greater torque. So the restoring torque, the torque that the wire applies, is minus kappa, this is the torsion constant, times theta. Okay? Theta is how much you twisted it. So, all right, so let me ask you this. For aluminum wire and a steel wire, which one will have the greater kappa? steel. How about cooked piece of spaghetti? Huh?
Compared to what?
What will the kappa be?
Very small.
Very small. It'll probably be 0. Okay. So now you know what that kappa means. Okay. It's the torsion constant. Stiffer the material, greater will be the restoring torque. Okay. All right. So tau is again, this is using Newton's second law. Tau, the torque is I times d squared theta by dt squared. And so this is equal to that. Kappa is positive, I is positive. I is the moment of inertia of this object about that axis. Okay. We'll call this omega square. And back, you got the same equation. Instead of for x, you got that same equation for theta. Okay. Yep.
In that equation, theta t is equal to theta.
This one?
Yes.
Mm-hmm.
Or the one below it. What is that symbol?
Theta naught.
WT plus,
Omega.
what's the other one?
Phi.
E.
Yeah. Okay.
And
Eg-
what does that value represent?
So again, remember, here's the second order differential equation. This constant is in the equation. But in your solution, there are two constants that are not part of the solution. And you got two constants because it was a second order differential equation. And those two constants can be determined by initial conditions. So for instance, you can twist it this far and not only twist it that far and then give it a velocity. Those numbers determine that.
Okay.
Okay. Let's say you twist it and let go, and then cosine t equal to 0 will be 0, and this will have to be 0 because you twisted it to theta naught and let go. So if you twist it to theta naught and let go, okay. So those are determined by initial conditions, by the position at time 0 and velocity at time 0. Okay. So, okay, again, so omega is that. Again, the period is, independent of the amplitude. I is the moment of inertia. So for rotational motion, mass got replaced by moment of inertia. And this is the torsion constant. Okay. Again, period is independent of the amplitude. So you could use this for a clock. Okay. You could use a torsional pendulum for a clock. Okay. Yeah. Here's a simple pendulum. Okay. If you disturb this object when it's hanging there, it's in equilibrium. When you disturb it, here's the weight of the object. And this component of the weight, mg sine theta, is restoring it. When it's over there, it's bringing it back here. Okay. So that is the restoring force. Mg sine theta is the restoring force. Mg sine theta, and that is equal to mass times the acceleration of this object. And we'll measure the configuration with this arc length. So it's d square s by dt square. The arc length is equal to the length of the pendulum times this angle. Okay, so d square, and we'll measure the configuration by this angle. Okay, so d square L by d L times theta. Okay, so what you get is d square theta by dt square. And as long as the angle is small, and you can test this out on your calculator, put it in radian mode. For small angles, sine theta is approximately equal to theta. Okay, so you can put it in radian mode and calculate sine 0.1, and you'll get 0.1. Yeah. So if you do the Taylor series of sine theta, okay, the Taylor series is theta plus and theta cube and so on. Okay. So if for small angle this is negligible and sine theta will equal theta. Okay. will be approximately equal to theta. Okay, so sine theta will be equal to theta. Okay, and so here's d squared theta by dt squared. G is positive, L is positive. We'll call this omega squared. Okay, so you get the same equation. All right. So really, we are cheating you. All we're doing is giving you one equation to study. All right. Here's the period again, independent of the amplitude. Okay. The period only depends on the length and g. So here's a famous thing. So you can make a simple pendulum, make it the L such that the period is 2 seconds. Okay. So every time it does half an oscillation, that's 1 second, and you can build a clock. Okay. In fact, I believe Galileo was the one who discovered the simple pendulum. Apparently, whoever it was, he was at church, sitting at church at a sermon, and a small earthquake happened, and it set the chandeliers in oscillation. And ever the scientist, he's timing it. And what he discovered was, as the oscillations died, it was taking the same time. Okay, so he discovered that the period was independent of the amplitude of oscillation. Okay. All right, so here's the physical pendulum, and you can take any object and pivot it about that point. The equilibrium position would be with the center of mass right below the pivot point, and if you disturb it, this torque, the weight times this moment arm, will make it oscillate back and forth. Okay, so the torque, the restoring torque is mg times the lever arm, d sine theta. D is that distance. Okay. So when will the restoring torque be 0? If you nail this at the center of mass, then D will be 0 and the restoring torque will be 0. And that's when it won't oscillate. Okay. And that makes sense. Okay. So again, the equation is, if you measure the configuration of the system by this parameter, d squared theta by dt squared is omega squared theta, where omega is mg dm. Mg is the weight of this object, d is the distance between center of mass and the pivot point, and I is the moment of inertia of this object about that point. Okay, again, this is a simple harmonic oscillator, and it's the period is given by 2 pi I mgd. Okay, so here's an interesting fact. We calculate this thing. Well, does this have anything to do with reality? So for instance, when you walk, here's a physical pendulum. You're walking, you can calculate the period of that physical pendulum, and you can calculate your walking speed. And that'll give you your normal walking speed, and you can do it for any animal, elephants, giraffes, and so on. Yep. And you can come up with people's walking speed. All right, now we've studied simple harmonic motion. It turns out that simple harmonic motion are related to uniform circular motion. So you have a satellite going around in a circle at constant speed, and let's say, so here's this ball going around at a circle at constant speed. Let's say you project the ball shadow on this surface. The shadow, this is executing exactly the same motion as this mass attached to the spring. This motion and this motion are exactly the same. So uniform circular motion is this simple harmonic motion plus this simple harmonic motion. you can project that motion on there, on this wall. Okay, so uniform circular motion is the sum of two simple harmonic motions. It's this simple harmonic motion plus this simple harmonic motion. Okay. So for instance, if you remember in the gravity chapter, we talked about how long does the International Space Station take to go around the Earth? I'm sorry? 90 minutes. And if you dig a tunnel through the center of the Earth, you'll take 90 minutes to complete one oscillation. Okay. So those two motions are related. All right, this, I'm not going to go over the derivation. Here's the speed of this object, okay? And that's constant. The velocity is changing. But if you take the x component of this velocity, there's that velocity, and that's exactly the velocity of this mass attached to the spring. Oops. There's the equilibrium position, and there's the... So the velocity of this guy at this location is exactly equal to this velocity. Okay. Similarly, so when an object is going in uniform circular motion, what kind of acceleration does it have? It has centripetal acceleration, and this component of the acceleration is exactly equal to the acceleration of that mass attached to the spring at that location. Okay. So there is that acceleration. All right, so what is it that you need to have for simple harmonic motion? A restoring force. And what should be the nature of the restoring force? Proportional to the displacement. Okay, so the restoring force needs to be proportional to the displacement. Okay. How about this problem? That's very hard. That's a nonlinear restoring force. Okay, and that becomes very hard to solve. Okay, so all we're doing is this guy. Yep.
Is the kx squared, is that like a double pendulum problem?
I don't know exactly, but double pendulum is not, I know it's double pendulum is nonlinear. Okay. Anytime you hear nonlinear, that means this, it's not this. Yeah. Yep. So any chaotic system, it's nonlinear. All right. Now that we become experts at simple harmonic motion, let's do the next complicated step. What's the next complication?
Friction.
Add friction. Okay. So we've studied this guy, and now we're going to add friction. Okay. So, and you want to change friction, it could, in water, it has a certain amount of friction. And if this was honey, the friction would increase. So you know how to change friction as well. Okay. So for instance, if this was the wheel, and that's what they do in your shock absorbers, remember? They put this, whatever is oscillating, in oil, and that adds damping. Okay. All right, so when you add friction, here's what happens. The amplitude of the oscillation dies exponentially. So there is the amplitude of the oscillation, and that dies exponentially. Okay. Now the simplest way to model it is, okay, we'll say that the friction force is proportional to the velocity. That's one of the simplest way to model it. Okay. So the D for damping, the damping force is proportional to the velocity. Okay. And the negative sign tells you if the velocity is in this direction, the friction force is in the opposite direction. And if it's moving in that direction, the friction damping force is in this direction. So, and that makes sense, you know. I mean, you've experienced this when you're flying through air, the drag force is always in the opposite direction. Okay. And so this is what we'll model. This will be our model. we'll come up with a solution and check and see does it match reality. And if it doesn't match reality, then you would have to refine this model. Okay? But we're not going to do all of that. We'll just assume that this. So this works closely. Okay? So here's our. We're going to add this friction force to our system. Okay, so we want to model this system. What is it that you're going to, what is it that you're going to come up with then? When you say you're going to model this system, you're trying to come up with a mathematical equation describing the behavior of this system. What is your ultimate goal? What is this guy? Okay. See, that's what my mother wanted to know, where I was at all times. Okay? That's what.
That's a good joke, Professor.
That's a good joke. You like it, huh? So that's what we want to know. All right, so there's the force. What is that? That's the force that the spring exerts. And there's the friction force. So there's the net force acting on the object. That's the total force acting on the object. And Mr. Newton tells us that should equal the mass times acceleration of the object. Okay? So here's mass times acceleration. There's kx. And velocity is dx by dt. Okay? And now we'll bring all of that on one side. There's that. Okay? And so now let me divide by dt square plus b by m dx by dt plus k by m. K by m was omega square. Okay. So here's the neat thing. Okay. If you want the frictionless model, all you do is put b equal to 0. Okay, so here's a differential equation with friction present. Okay, so here's this mathematical model describing the behavior of this system. Okay, if you put b equal to 0, then you get back your old system. If you put b equal to 0, you get this system oscillating in air. Okay, so that frictionless system is a subset of this system. Okay. So the more complication you're adding, the simpler systems are all subsets of that. Okay. Okay, so you'll learn how to solve this differential equation. It's slightly more complicated than the previous one, but again, it's still solvable. Okay. And here's the solution. It looks very similar to the old other solution. The only difference is this guy, this exponential factor. Okay, and that is coming in the amplitude. So the amplitude is exponentially decaying. Okay, here there's one other thing that changes. When friction is present, the period of oscillation changes, the frequency changes. Now you see the frequency. This was the old frequency. Okay, that was the old frequency square. And now the frequency is changed by that much. The frequency is decreased, and that makes sense. Without friction, it was oscillating 10 times a second. With friction present, now it's oscillating maybe 8 times a second. Okay. All right, and well, this also gives you an idea. Let's say this was your wheel on your motorbike and you hit a pothole and you don't want the wheel to oscillate. What do? You just make sure B is large enough such that this term cancels that, and then it won't oscillate. Right? So that is called critical damping. Okay? Of course, if that gets to be too large, then the wheel might not even get to the road. You don't want that happening either. So you make sure that that B is slightly less. Okay? So anyway, so this is critical damping. That's the value for B such that that wheel comes right back to the road. This is B less than that, and so you have some oscillations. And this is B is too large and the wheel is not even coming back to the road. Of course, you don't want that. Okay, so this is critical damping. This is under damping, this is over damping. Okay? Anyway, so this is the frequency of oscillation without friction, and with friction, the frequency of oscillation decreased. Okay? Okay, what did friction do? I'm sorry? It-
Bleed off energy.
Yeah, it bleeds off energy. So every oscillation, it bleeds off a certain amount of energy. What if you decide you'll put an equal amount of energy? Let's say it bled off 3 joules of energy per oscillation, and you put 3 joules of energy. It'll keep going. How long?
Forever.
Till as long as you keep putting that energy. Right? So you can compensate for that. Let's try and do that. Okay? So now you're forcing the oscillation. Okay? So if it's possible to compensate for loss of energy in a damped system by applying an external force. Okay, so that's what happens, you have a child on a swing in a park. You set him in motion, and then the child starts crying. What do you do to shut up the child? You push. So that's what you do. All right? We're going to compensate. All right, so here is the spring force. What is this? That's the friction force, remember, damping. This is going to be you pushing the child. Okay, so this is an external force you'll apply. There's the amplitude of the force. So now we're going to drive, okay, and that's the driving frequency. Okay. That's the frequency at which we apply a force. This is the net force, and so Mr. Newton tells us that's equal to mass times the acceleration of the object. And again, this is a much more complicated equation, and here is the solution. Okay. So this is the frequency of oscillation, and this is the driving frequency. Okay, and so now we'll give you an expression just for the amplitude. Okay. And now the system is oscillating at the driven frequency. You guys remember when we went to the physics lab, we put that plate on an oscillator. That plate was oscillating at the driven frequency. Okay, in physics 2, we'll do a lab where you'll drive an oscillator and the system will oscillate at the driven frequency. So for instance, this table has a natural frequency. Let's say this table wants to oscillate at 50 hertz. And if I hit it at 40 times a second, it's vibrating at 40 times a second. It doesn't like it, but that's the driven frequency, okay? So here we go. Here's the amplitude of oscillation. There's the amplitude of the force driving it, amplitude of the driving force, mass. Here's the driven frequency, driving frequency. Here's the natural frequency. So there's the amplitude. Just one second. And look at this expression. See, when the driving frequency matches a natural frequency, what happens? This goes to 0. The amplitude becomes large. That's called resonance. Yep. Mm-hmm.
With the example you made, you said the original frequency of the table was 50,
Yeah.
and the driving frequency was 40.
Yeah. So, what I'm saying is every object has a natural frequency. Let's say the natural frequency of this is 50 hertz, which would be that number.
Okay.
And if I hit it at 40 times a second, this driving frequency is 40.
Oh,
Okay.
okay. I thought you said that. I thought that the driving frequency would like cancel out the.
Well, no. So the driving frequency now it's forcing the object to oscillate at 40 hertz.
So the original frequency is kind of negligible, or what?
So what happens is There are several modes that come into play and they combine and they're making it oscillate at 40 hertz. Yep.
Is that constructive or destructive
Interference.
interference?
So it's sort of destructive interference, and that's why you can't set up large amplitude oscillation. And I'll show you a applet in a second, okay? Okay. So when the driving frequency matches a natural frequency, you can set up large amplitude oscillations. And that's what this is showing you. See, when the driving frequency matches the natural frequency, see, you can set up large amplitude oscillations. And if this amplitude of oscillation is large enough, it can destroy a system. What is this graph showing you? See, this is damping. When damping is large, you can tame the oscillations. So that's what you have to do. In a bridge, do you want the bridge, the wind to destroy the bridge? No. So as an engineer, what you want to do is you want to put large damping in there. Okay. So let me, you guys, you have to, okay, so let's do this first. Okay, so here's a system. Here's the system. This has a natural frequency. And what we're going to do is we're going to grab onto this spring and pump energy in. It's like pushing a child. That will be the driving frequency, okay? So right now, we'll do it for this. The driving frequency doesn't match the natural frequency, and let's see what happens. Okay, so right now, the driving frequency is not matching the natural frequency. So you're not pumping energy at the right time. It's like pushing a child, but except that pushing it randomly. Sometimes you're pushing the child when the child is coming at you, and so you're slowing it down. And sometimes you're pushing the child when the child is moving away from you, and the push is not as effective. You're not pumping energy. Okay? All right. Now watch this. So what the heck? Okay, so now the driving frequency, I'm going to match the natural frequency. So every structure has a natural frequency. Okay, and watch it. My driving amplitude is still going to be the same, except that now the driving frequency is matching a natural frequency. So now I'm pushing at the right time. Even if I give a little push, if I give the child a push at the right time, so I'm putting energy at the right time, and that energy can build up. If this were a bridge, you can say goodbye to it. Okay? If this were a tall building, you can say goodbye to it. And this really happens. You guys must have seen.
This is the garden hose nozzle my team spent 3 years building because every pressure washer on the market kept letting people down. Every pressure washer has the same fundamental flaw.
Okay, you guys must have seen this movie. So this was built near Seattle, Tacoma, Washington. This was built in the 30s.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So you saw that. So what was happening was the following. Roughly this. So here's a top view of the bridge, and here are those pillars at the bottom, and wind was blowing. So you heard that only 35-mile-an-hour wind, and vortices would build up behind the pillars, and they would break away. And they broke away at a frequency that matched the natural frequency of the bridge. So you set up resonance. And you saw that when you shake, when the driving frequency matches a natural frequency, you set up large amplitude oscillation. And see this kind of stuff, they built a walking bridge in London in 2015 or something like that. And even now it happens. So the first day, everybody in London wanted to walk across the bridge. 3,000 people got on the bridge or something, started shaking too violently. So they didn't put enough damping. Yep. Mm-hmm.
So you were saying those pillars,
I'm sorry?
you were saying that the pillars were essentially a damping force?
No, that's where it's like when you're pushing the child, you have to push the child. So the wind was pulling on the pillars. Every time the vortices broke away, it's like they're pulling this pillar. It's like pushing, or you can think of it as pushing the pillar. Hitting the pillar like that. Here. Okay. See, I push this, right? Yeah. Okay, so so what does the word resonance mean? If an external force drives at a frequency that matches the natural frequency. So your driving frequency is matching the natural frequency. And then what happens? You can set up large amplitude oscillations. Why do you set up large amplitude oscillations? Because you're pumping energy in at the right time. And you can build up the energy of the system. Because you can pump in a lot of energy in the system. And so you can set up large amplitude oscillation. So you can get a child to swing with large amplitude by pumping energy at the right time. If you pump energy at random times, you can't set up large amplitude oscillations.
Does that mean the work is,
I'm sorry?
like work done is minimal at this time?
Yeah. Okay. So it's like saying, I can make you rich by just putting in 5 cents each time. You know, as long as that 5 cents is greater than the 3 cents that you're spending every time I put in the 5 cents. You guys have heard of people breaking wine glasses by singing?
Yeah.
That's the same thing. Yeah. You can put in energy any way you want. Okay? You have to put it at the right time. Okay? So if a frequency matches the, so this happens all the time. Okay? So for instance, the natural frequency of buildings depends on the size of the building and so on. Okay. Now here's the deal. If an earthquake happens, it'll shake the ground like that. If this frequency matches the natural frequency of one of the buildings, then that building will collapse. And if this frequency doesn't match the frequency of that building, building won't collapse. Okay, so this happened. So in the epicenter of the quake in 1985 in the western coast of Mexico was 400 kilometers from Mexico City. Angular frequency of the seismic wave that reached Mexico City were concentrated at 3 radians per second. So in one oscillation is 2 pi radians, so that's 6 radians. So it's oscillating, the ground was oscillating once every 2 seconds. Okay. Taller and shorter buildings survive. So it was oscillating once every 2 seconds, the ground. This didn't match the frequency of this guy or this guy. It matched the frequency of this guy, and these guys collapsed. These guys survived in the same region. So these guys, all these tall buildings, they experience, the taller you are, the greater the wind speed, and they experience winds. Okay. Do you want this to collapse like the Tacoma Narrow Bridge? No, of course not. And you have to put in damping. Even with damping, this guy can oscillate. The 206-story Burj Khalifa can sway up to 2 meters at the very top. At the very top, it can sway this much, 2 meters. This is a meter. Here's 2 meters, up to there. How do you want to own the top floor? And you only paid $100 million for it, remember? And as an engineer, you got to make sure that my coffee doesn't spill. I'll be super mad, but anyway. Well, I won't be because I don't have the 100 million, but see, she's happy about that. Now I was going to buy her pizza too.
Pay for my parking ticket.
All right, so here's one way to put damping. So this building is in Philadelphia. On top, so there's a water tank. Okay, and when this building shakes with the wind, see, when the building shakes like that, the liquid is the liquid can't keep up with it. So the liquid is oscillating at a different frequency than this, okay? And that's providing the friction, and that's providing the damping. Yeah. So this is a 300,000 gallon reservoir. Yeah. Okay. Here's the damper in the tape.
What would you tell a man who can scroll for hours but can't work for 10 minutes?
Okay, anyway, this is the damper in one of the tall buildings in Taipei. Okay. All right, so